Hello, so how are you? Oh, what is your name? This and this your name? Great. So what you can do is simply pin down your name in the comment box, and then we are going to take your name in the next video. It would be fine. And also pin down your any questions, any query regarding the lecture. It would be very fascinating to have some conversation with you, and we can establish a very effective communication. It's the communication should not be just only one way, but in both the way. Therefore, I'm asking you to pin down your name as well as whatever the questions that you have. Okay, as you have probably seen, the thumbnail of this video is classical mechanics. Yes, this is quantum mechanics, but this is the very beginning of the quantum mechanics, and the beginning is with classical mechanics. Why classical mechanics? Because before quantum mechanics, before the invention of quantum mechanics, there was only thing we had is the classical mechanics. So now we have classical mechanics. I want to understand what happens at the molecular level. Therefore, I would like to know how we can transform our ideas from classical mechanics to quantum mechanics, right? And this is essential. I told you in my previous video that if you want to become a scientist or you want to develop your own theory, you have to trust or you have to question whatever has been done previously. You have to also understand that why something works, what are the limitations of previous theory, and what are the loopholes. Basically, you are an investigating agent who is investigating something which is not working and something that should work, and gonna explore many important things which is still mystery to us, right? That's why we assume that we have not yet found the theory of quantum mechanics. Therefore, our best practice is to understand what's happening with the classical mechanics. Let's get started. So when we talk about classical mechanics means that things that are pretty much classical, things that we observed daily, right? Classically, you can see the ball is moving, the ball has certain velocity, and it follows certain law, and these laws can we understand from Newtonian's perspective, right? So Newton was first to comprehend using mathematics to describe these motions, that why something happens and there is a force acting on each and every particle, and if you have a certain force going on any particle, this particle is going to be accelerate, and this is one of the most fundamental thing. Now here Newton first didn't say that what type of force is going to apply on this type of object. He just said that if any force is going to apply on the object is going to accelerate, right? Now, in a simple case, let's say that force is kind of a constant force. Any force, I don't know what is the source of this force, is constant. Therefore, your mass times acceleration is going to be constant, right? No change in over here, therefore no change in this way. Now, if you know this one, you have another definition of force, that force is basically the rate of change in momentum, right? Considering that the mass of an object is not going to change, the momentum is defined as product of mass times velocity, okay? Therefore, if I just take a time derivative of this guy, I will take mass as a constant, and this becomes dv over dt. But wait, I have assumed that force is a constant, therefore A is going to be constant, but V should not be constant, and this is equal to m times A. And over here, m is not changing with time. If m is changing with time, we have some certain different formula, right? So if you have this situation, I simply understand dv over dt. And if I just integrate it, you will realize that V becomes u plus at. Oh, these are the equations of motion that we have already understood in our class 9th. Similarly, I have something x is equal to ut plus half at square, initial velocity times time plus half into acceleration times time squared. Great. So what does this basically tell you? It tells that if you apply a force, a constant force, on any object, the object has certain trajectory. This is basically tells you the trajectory. Trajectory means the position of an object. So in order to locate the position, what we can just say that, okay, I have some coordinate system, and since object is restricted to move in certain particular direction, there is no any, two-dimension axis. Therefore, we have only one-dimension axis. Let's assume there is a velocity v, and this velocity is changing uniformly. Therefore, acceleration is constant, right? Not acceleration, velocity is changing with time, but acceleration is uniform, right? Acceleration is going to be constant. Hence, I can predict the location at every time. And this is kind of very important stuff. But what you have to find over here, that we are solving this by assuming that whatever the force that is hindering upon the mass or acting upon the mass is basically a constant, right? Newton did not say that, wow, how we can figure out the force. We have different circumstances where we can assume the force. In one circumstances, we have said that an object can be acted on any type of force, and this type of force has a nature that it's going to be remain constant at particular interval. Therefore, I can easily find out what would be the trajectory, and this trajectory is important, trajectory and velocity, and I can predict everything about the motion of an object. That's incredibly fine. But who is going to tell me what is the nature of force? And he said that, okay, I have another theory, and the theory is called theory of gravitation, right? He said that on observing the apple that is falling from the tree, he said that there is a force of gravity acting on it, and it's not on the apple. It also acting similarly on the moon, because moon is falling on the sun, on the earth, and similarly earth is always trying to fall on the sun. It's basically the effect of gravitation. In gravitation, two objects is always going to attract, always going to fall onto each other. But we can see the motion of only one particular object because of this small thing, that let us say that if F is equal to m into A, any force is acting, and this force is proportional to m times m over r square. Let's say m is the mass that is falling on any object. Therefore, I understand that m is very heavier than this one. Therefore, if I just see from here, I can observe that, oh, all right, since m is very greater, r has some distance, no problem, and g is there, therefore I got some finite value of A. On the other hand, if I just apply the same thing on heavier object, let us say that F is there, F is the product of this one, this is not going to change, and considering it to be m into A, let us say A, it should be some prime, A prime, right? And I say that, okay, I have this again formula, m into A prime. Over here, m is extremely small. Therefore, this number is coming out to be very small. Obviously, it is finite, but very small. Therefore, whenever we look at something which is bigger, for instance, we have sun, right? Sun is extremely bigger than Earth or any other planet in the solar system. Therefore, whatever we are seeing, that all the objects, all the planets are moving towards the sun, moving as if they are falling onto the sun, right? This is his idea. He said that, okay, I am giving you. You want something? I'm going to give you this one. F is equal to gmm over r squared. Incredibly good, right? But certainly this framework has limitations. First limitation you understand is here, Newton did not tell you what is the force. He simply told you have to figure out by your own self, by either experiment or if you have any intuition and so on. People were very happy up to that time, right? Because afterwards, Coulomb came, did some experiment, charge was discovered, and he said that if you have certain charged particle, it is having the formula similar to the gravitation, and we call it as a Coulomb force. And hence, we have certainly electric field, there is electric force, and all the phenomena. And again, if electric force is applied onto any particular mass, let us say I have a charged particle of electron E, Therefore, this Fe is going to be the mass of electron and A of electron equal to kq over r square. And when we compared gravitation with Coulomb force, it found out that gravitation force is extremely weak, which is minus 10 to the minus 40 times F of E, right? We can avoid the force of gravity in that case, in that scenario, and we can simply work out with the interaction. Not only that, afterwards, people have discovered that there is also a magnetic field. A magnetic field is basically nothing but a electric field. And we have the combined force formula due to the Lagrange, that which it's simply stated F is equal to Q, V cross B, and plus E. And this encapsulate all these things. This is due to magnetic field. This is Coulomb force, electric force, right? Or electric field. Therefore, you have to rely on something very intuitive thing, that I am doing probably some foreign experiment, and from that foreign experiment I will somehow get something, and from there I can predict the equation of motion, and I will do the experiment to confirm, okay, we are finding something. And once we know the force, I can easily know what is the trajectory, and trajectory is most important, you have to understand. And once I know the trajectory, that is the most important part, I know what is the momentum, right? There is no problem. And these are kind of very basic thing we want to find out, right? Why they are very basic thing, and why we want to find out? Because if I know what is the dynamics of charged particle, how the charged particle are to move, I can predict that how is the behavior going to change as the time will progress. Great. And this is the predictability of the physics that we want. That's why we have developed a mathematical language that has empowered us to understand what is happening in the nature. And from there, we can demystify something is there, something isn't there. But the trouble starts when we use this same principle, same laws, and we want to investigate what happens to the gaseous particles. And it was started with the hydrogen atom. When people have taken some gaseous particle, that is, let us say, gas is made up of hydrogen gas, and they observed some type of spectrum. These are some energy spectrum, and they could not understood that why this energy spectrum coming out in a discrete way. There is energy. Let us say we have talked about energy in classical mechanics. Energy is kinetic energy, which is basically half mv square, and there is another form of energy associated with any type of force that can store that amount of energy, which is come to be potential energy. So if you have gravitational force, therefore there associates a potential energy called mgh, right? And so on and so forth. Similarly, we have potential energy corresponding to electric force, magnetic force, nuclear force. So whatever you have the force, you will have the potential energy. Basically, what potential energy tells you that how something is interacting. But people didn't understand in that way that, okay, something has to be interacted and so on. Therefore, they were talking about the force. If there is a force, therefore, obviously, any particle which is moving will have kinetic energy. But the more fundamental thing is that there is a energy associated with all the forces. Means that if you climb up the mountain, you are getting tired and potential energy is storing because you are doing work against force of gravity. If any charged particle is doing work against force of electricity, then it stores the amount of energy. Similarly, we have elastic energy. If any particle, any mass is doing some work against the will of the spring, you have elastic energy, which is basically half m any particular distance, that is x, or any particular separation by x, half mx x squared, right? Sorry, half kx squared. It's very incredible. These things are there. These things are chunk of particles are there. And one of the important part that is governed by this one is ma. F is equal to ma. This is incredible because just plug in the force, you can easily predict what is the acceleration, position, trajectory, momentum. If I'm not starting with the force, if I just start with the dynamics of x and p, and somehow I know what is the relationship between them, I can easily find out the forces. It should be, right? But the problem is that we weren't able to do it when we studied the hydrogen atom. If you look at over here, the energy, if I just plot the energy graph, you see that energy is going to change with h. The potential energy will increase as h is increasing. Energy is going to be increases if I just plot E and V, isn't it? I know in this behavior, energy feels like continuous thing. It's changing continuously. If I am increasing the velocity, energy is continuously changing, continuously increasing. But what happens with the hydrogen atom? People could not comprehend this situation using the Newtonian formulation. Why something happens? This was the another experimental evidence people had that we are hitting the limitation of this theory, right? But people have came that okay, we can save it, and thanks to the Bohr, he said that there is some kind of orbit inside the atom, and this orbit has some particular energy, and whatever the energy we are thinking in terms of classical, it is not going to be there. Energy is going to be quantized. Energy depends on number of orbits in which electron is in. And the motion that we are thinking of the electron inside atom is kind of very weird. We should not think of it like Earth is revolving around the sun. So it was Bohr, but we didn't have any kind of formulation that how quantum mechanics had evolved, how to do it, and so on. So I have given you that, okay, there is some kind of experiment which tells us that energy is quantized. Energy is kind of 1, 2, 3, it's not continuous. So how will you propagate from this picture to quantum mechanical picture? Maybe you know what is the quantum mechanical picture, right? This is the problem. So let's come back to our situation here. What was the situation? Situation is that you need to tell me what is my force, and then I'm going to tell you what would be the position and momentum. It's not going to be too easy if you will give me the trajectory, the momentum, and I can tell you, okay, this could be the force. And this is kind of very limited. The limitation itself there that, yeah, I have to somehow know the force. But people have done a tremendous job. They found out electric force, they found out nuclear force, magnetic force, gravitational force. And so far, these are the fundamental, you may just say that, and there is called weak force. These are called the 4 fundamental force that govern the universe. We don't know yet. Another could be 5th force, yet not discovered. But when we are studying cosmology, we have certain crises these days. These crises are called dark energy and dark matter. Something which is related to maybe some new postulates for some force. There is some force out there. But that is an interesting story. There is an interesting aspect of a story which I am not going right now hitting there. But I am basically hitting at some point, at some limitations, that if I don't know the force, I will not able to know what would be the interaction or what would be the energy associated with it, because the potential energy is kind of very important. It's going to tell me that how much work done has been done against this force. It means that some energy has been stored, right? Therefore, afterwards, in during 1800, like 1850 and so on, you can check the Wikipedia, there comes a guy. He said that, you see, imagine things like that. I have an object. An object is falling from A to B. What type of path it going to choose? Can you tell me? Yeah, your answer would be probably that straight line, no doubt. Who told you straight line? You may say that, okay, I know what's F is equal to mass times acceleration. this guy is under the force of gravity, assuming there is only gravity, there is mass m. Classically, we are doing the experiment. And I can, since force is going to be constant, this becomes ut plus half gt squared. And this u is basically 0 over here. I got half gt squared. With the time, it is changing like parabola. X is 0. Over here, the position is changing like quadratic way. With time, it's changing quadratically. And if I plot everything, I can easily find out what is the trajectory of the particle A to B. But let's say I don't know what type of force is there, then what would be the trajectory? You may say that, okay, in the absence of force, I don't know what would be the trajectory. And let's say that I want to predict the trajectory, then there could be many possible trajectory, right? The particle can go from here to here, here to here, here to here, maybe a straight line, maybe nearby a straight line, and anything possible, right? Yeah, certainly it's possible. What would be the best trajectory? Who will gonna tell you? Then you say that, okay, I don't have any other way to tell the exact trajectory. I have only one thing to tell, that if you give me this equation, I can tell you what is the best trajectory. Because this formula is filtering out all the other possibilities that a particle can take. And it gives me that this is the only possible trajectory that particle can take under this influence of the force. Exactly. Right? It means I have to give you the force. And there are no other possibilities. Once I fix the force, there could not be many other different possibilities. But if the force is not decided, I can think of it that there could be many possibilities. Now you do the experiment. If you do the experiment and you have done this several times, you find that this body is actually following some particular path. And I have a computer and I am trying to simulate these total paths. That, okay, fine, I want to, let us say that this black curve has a true path and these red ones have some kind of a simulated path. What is the relationship between these paths? And I found out that somehow it minimizes. Comparing to these trajectories, the time minimizes. And we understand from the light principle that a light is propagating from A to B always follows that path that takes less amount of time. That is very amazing. It means that can we something say that, all right, no matter whatever the force you have, instead of gravitational force, I can take Coulomb force, maybe a magnetic field force, and I can always plot the trajectory, and I always end up with something that, okay, if I compare those trajectories, I found only those trajectories where the amount of time that is taken is kind of minimum. That's truly amazing. It means that this object, whatever it is, in nature, something is there that governs in such a way that which tries to minimize some possibilities. All right. There could be hundreds of possibilities. Out of these hundreds of possibilities, I only wish for only one possibilities that is going to be minimal compared to this one. Right now, my terminologies are very vague, right? I'm emphasizing on minimizing, but it should not be just only minimizing, but I'm just, giving you the hint that, okay, what I'm trying to do is that, can I bypass this notion? Therefore, I have to understand something. So let's do an experiment and I toss some particle and try to do, if I toss a particle, what I'm just going to getting, I will get the trajectory in some space. Let's say I'm in two-dimensional space, x, y. What will I actually plot? I will plot it at every instant what would be the location of the body. At some time, the location is over here, over here, over here, over here, over here, maybe over here. This is how your particle is look like. Out of many trajectory, there is only one possibility. So now as we have this trajectory, as we have these plots, I am just, countering the location. What does it tell me? What kind of information that it contains? With the information of location, that is I have, let us say this position, one thing I for sure, if I will measure the time, and somehow I will also know that at which velocity it is traveling, right? The coordinates are much more important. If you know the coordinate, if I know what is my x-axis, y-axis, I easily know, because the velocity is not going to be changed. The velocity is going to simply dx over dt and dy over dt. So if I know how the points, how the location of any particle is changing, I eventually know how the velocity is also changing, right? So what is kind of very fundamental is the trajectory. If you know trajectory of any particle, I simply understand what would be the velocity. Therefore, I must take some kind of a snapshot, and I will have a space where particle is there. Particle has certain information, and this information contains these things, x, as well as I can easily find out the velocity. And if I know these two important quantities, I can do most of the things. I can find out momentum. I can find out how the momentum is changing with time. If I find the momentum, how the momentum is changing with time, I can easily comprehend how the force is going to be. What would be the force, right? Not in the perfect way, but in some particular manner. And I know that if you just do this kind of experiment, the object is actually going to take only one particular direction. One particular, the choice of all the possible trajectories, there exists only one trajectory that could be it, that is going to follow this equation f is equal to m times a for classical object. Therefore, people came up with a concept is called action. Now, I am not going to go in detail what is the history of action and so on. But what I am just telling you, because it's just for the another series which I'm going to cover soon, once I finish with this series, it's going to be a classical mechanics series, the advanced classical mechanics series, in which my first approach would be that comprehending classical mechanics from action principle. All right. People formulate that action is going to be minimized in order to predict the true equation of motion. The true equation of motion will automatically, if you just minimize this action, you will comprehend this force is equal to m into a. Automatically, the action will give you the equation of motion for a classical object. How? It says that action is going to be something integral, an object that is called Lagrangian, and this Lagrangian is a function of position and velocity, and it could be the position of time. All right, and this is going to be multiplied with, what I have to do is that, as I told you, the coordinate system is going to play more important role. Let's say that any particle is from here at certain time interval, another particle is over certain interval. I have some coordinate over here and some velocity over here. It says that, you see, From A to B, there could be many possible trajectory out there. Given the velocity of the particle and so on, there could be many possible trajectories a particle can take for, let us say, Ti to T final. Then what would be the only one trajectory that is going to give its equation of motion? It then formulated that what you have to simply do is that you take little bit of perturbation of the trajectories. And this trajectory is the information that its trajectories have will contain some kind of a mathematical function that has the information of that has its information encapsulated in this function, which is a function of position and its velocity. For a moment, I'm just leaving this t right now. Position and its velocity. And this guy, together with time, t, called the action. And it, in textbook, you find that this action is represented by this s. Between the time interval, you have this position, this velocity, and there is time t. And another thing that is important is that if you want to vary this action must be minimum, it may be a maximum, or in some sense, it has to be stationary. What does it simply mean? That if you perturb the true equation, true trajectory, it must come back to its original position, right? If somehow it is going to come towards this original position, right? Because assuming that this could be just only one trajectory, I am giving some kind of perturbation, it has to be stationary between these time intervals, and that would be its true equation of motion. Minded, these are very vague type of analogy that I'm giving. It has more deeper framework because these are basically called phase space and configuration space, which I'm going to talk about later on. But just give you understanding that, okay, what happens? You do some experiment, you have some kind of, information regarding its coordinates. If I know the coordinates, how the coordinate is changing, I simply know the velocity. So I have the construction that, okay, I have this A to B, how the particle is going to be, move from A to B. It requires the position and the information regarding velocity. Therefore, there could be many possible trajectories that it can go, right? Or there can be more possible trajectory between it. And these possibilities can be encapsulated in terms of an action. So what I can just do is that, give some little perturbation to this action, and making sure that this action, the variation of this action has to be zero. It has to be extremized or stationarized. It could be minimum, it could be maximum. You have heard that, all right, if you have any function, the function can be maximum or can be minima depending on its derivative. Derivative, let us say, with respect to x is going to be 0. Depending on, I can take the second order derivative equation. Either it could be greater than 0, it could be less than 0, or it could be maybe completely 0. In that case, I'm not going to be able to tell. But when this function, that is, let us say, some kind of function, is the first derivative is going to 0, at that point the function is not going to have more changing. It's like that it has some minimum change that can occur if I just do some kind of perturbation to it. Similar analogy has been given to this action. Take this action, fix the time period, and see whether this action is stationarized or not. And the way to get the stationarized principle is just the variation. This is called delta. Delta S is equal to 0. So, well, how can I find out? It says that, all right, I will take delta S, and this becomes delta of Ti to T final Lagrangian x dot, and there is dt. Impressive. Now, since delta is again some kind of a change, and these are differential operators. What you may see that these are also a differential operator, right? Inverse of derivative is basically integral, and these are called linear operators, so I can easily exchange it, and hence I can write it like delta of L dt. Now whenever you have this change in Lagrangian, I can always write it like this: delta L over in partial derivative, because this is a function of x and x dot, delta x, and there is kind delta x, right? Similarly, I have delta x by delta x dot, and you may say that right, this is the action. Now what we can do, I have certainly we have ti to t final. Now I have this delta s integrated this whole function with time delta dt, and I am saying that this has to be somehow 0. But here we have two objects, delta x, and this is delta of x dot. And here what is x dot? X dot is basically dx over dt. This is representing the velocity, correct? So let me just write in this way. It's purely mathematics. Delta x dot, and I have this delta, right? So what I can just simply say that d by dt of delta x. As I told you that d by dt is a differential operator, delta is also is a linear operator, and hence I can write this way. All right. Now, what I can just do over here is that delta L over delta x dot d by dt, right? Here you can see there are two quantities over here. One quantity is this guy, another quantity is this over here. Now, I have this delta x. Can I somehow take delta x as a common? But the problem is that I have this d by dt. Therefore, I have to get rid of this. And how we can get rid of this? If you have two quantities, let us say a, and there is dB over dt, then what you can simply do is that, okay, I have these two quantities. Let's take a time derivative of this thing, d by dt of both the thing. I will have do by dt times b and b dA over dt, right? Now you see that I got this guy over here, a dB by dt. Sorry, a dB by dt. Where is it? Sorry, am I wrong? dB over dt. Therefore, I can simply write it as a full time derivative minus which has not been taken time derivative. So similar thing I can do over here. I can follow delta s is equal to some time derivative dt right over here, del L over del x, delta x plus d by dt over everything, del L over del x dot, delta x minus, because it's going to be over here, therefore there is negative sign, d by dt on this guy, dl over del x dot, sorry, delta. And the b part is not going to be go anywhere. A and b. I have delta x. Hurrah! I got it. Now I got two terminology over here, that this guy, where I can take this derivative delta x. So I have now two integrals where delta L over delta x minus d by dt of del L over del x dot, sorry, delta x plus dt d by dt del L over del x dot delta x. Now, what is the advantage of this? The immediate advantage is that this is going to cut out each other and the integral is happening. It becomes a complete integral, right? Which is going to be between ti to t final. And this guy over here, another thing that is working over here, that whatever you are seeing this delta x at the boundary, because when you do the integral, this integral is happening at these boundaries, means that I have this trajectory over here with me, and this is corresponding to ti and this is t final. Whatever the integrand that I got, it's basically over here, and I have this delta x over this point and delta x over this point, and you see that you have this kind of thing. This delta x not going to say show any change at these 2 points. Delta x basically variation in x. What is the variation you are going to see over here? It's 0. The variation you can see at these points, but at the end point there is no variation. Therefore, this guy at the specific boundary vanishes, right? Therefore, I got only this situation. Now this is under control, because over here I got dt, there is del x. Another thing I told that, well, whatever the action that you have taken, you have the variation, and this variation must be 0. If this is 0, what does it imply? It implies that this whole integral has to be 0. How come this integral has to be 0? It can only be possible if I got delta x over d by dt minus del L over del x dot. That's going to be 0. It's incredible, isn't it? It's way incredible, because if I know what is this L, I can easily have this one particular equation, and this is basically called Euler-Lagrange equation. And this has come from one of the things that we have assumed, that the Lagrangian that has this information of particles' position and the velocity, right? If I give you the information that has some kind of function, then I got this Euler-Lagrange equation. But the question is that, what's the use? What is the basically how we can write? You said that, okay, Lagrangian depends on some function x and x dot, right? Then what would be the Lagrangian? Historically, Lagrangian has been defined, which I'm going to show you maybe in my classical physics lecture, that Lagrangian is defined as kinetic energy minus potential energy, right? So Lagrangian is a terminology irrespective of whatever system you have. It is defined as the kinetic energy minus potential energy. Give you an example, simple example. Let us say that a particle, a free particle, which does not have any kind of interaction. I told you that if there is a force, there will be some kind of work. If a body has carried, then it actually gives you the potential energy, the storage, the amount of energy that is going to store, right? Consider there is no force acting on it. I can say that this is a free particle, right? Free particle to move anywhere. There is no force, hence F going to be 0, right? Well, I have to see. Now, what I'm going to see over here, that okay, there is a particle, it has some velocity. Velocity is basically x dot. Since it has velocity, it's going to travel some distance, therefore x is going to change, right? So I can easily write half mx dot squared. No problem at all. And what becomes u? No potential energy, u becomes 0. L would become half x dot squared, mx dot squared, correct? Now, two things you have to remember over here. When I consider x and x dot in this Lagrangian, then mathematically I can treat x and x dot as an independent quantity. You must see x as some quantity A and x dot some quantity as B. You should not say that, oh, I have x and x dot, they are kind of related. They are related by time derivative, but they are kind of independent for this function, right? So what I meant to say is that if I will take del L over del X, and let's say that L is only a function of X dot, then this becomes 0. That is I meant. You should not say that, okay, L is depending on X dot, therefore I will first take d by dt somehow, because I should not, take like del by del t of L, and then therefore del t by del X, and since del by del L over del t have X dot, therefore, this is going to be L dot, and therefore I have inverse of X dot. No, you should not do this. Therefore, this Lagrangian has one particular structure, is that this Lagrangian has two quantities, a quantity coordinate, a quantity its velocity. And these should be treated as independently. Therefore, once I take a derivative with respect to x, and if L is only a function of x dot, the output I'm going to get is 0. Right? It's very incredible. So what happens with the Euler-Lagrange equation, if I see over here closely, del L over del x minus d by dt del L over del x dot. And Lagrangian is t minus u. T is basically kinetic energy minus potential energy, and for free particle it becomes mx dot square minus of 0. Therefore, my Lagrangian is now only a function of x dot square. Hence, if I just find del L over del x is going to be 0, just 0. And on finding del L over del x dot is going to be del L over del x dot half mx dot square. Now you will ask that how we can take derivative. X dot is dx by dt. You must forget about x dot. You can just say that, okay, this is basically b, and this becomes b square. Right? It will become m 2b over 2 m, and since b is basically x dot, it becomes x dot. That is how you have to take a derivative. Do not think too much. And now what you got? You got a very incredible thing. I got this is 0 is equal to mx dot is equal to 0. What does it imply? It implies that mv, oh, sorry. d by dt of mx dot is going to 0. Right? It's very incredible, right? If I look at this equation, f is equal to m times a, also maybe f is equal to dp over dt change in momentum, which is dv over dt, and let's say there is no force acting on it, dv over dt, right? That's incredible. What's over here? X dot is v, m v, and there is d by dt. M dv by dt is what? It's basically a force. So what you meant is that in this Euler-Lagrange equation, over here, this guy, for a free particle that is moving, it becomes a force. Isn't it? And it simply means that when I just took it, del L over del x dot, it becomes momentum. And in terms of pure terminology, we say that this becomes a generalized force. This becomes basically generalized momentum. And hence this equation at is equal to 0, therefore it says that del L over del x is basically giving you the force, the generalized force. Hence force becomes del L over del x. So if I have, it is just for this equation. Let's say the kinetic energy for anything is not going to change. It's basically mx dot square, but u can depend on, let's say, x. So L becomes half mx dot square u of x. I have del L over del x. It becomes del u minus del u by del x. Del L over del x dot, it becomes mx dot. Applying the Euler-Lagrange equation, it becomes del u over del x minus mx dot, basically d by dt. right? Now, what I'm going to get? I will get d by dt of mx dot is equal to minus del u by del x. It says that if I just say this is the force, force is equal to change in the gradient of potential energy. What are you telling me? I have not seen this equation. It should not be. You say that force is equal to mass times acceleration. How you have just said that if d by dt of mx dot is force, force is equal to gradient of potential energy. I can't understand this guy. Well, you can. How? Look at over here. F is equal to what? Let us say I'm taking about gravitational interaction or gravitational force between two particles over here, and let's say that m is our test particle. I got m. Sorry, I can easily find out g is equal to gm over r square, right? Acceleration due to gravity, very fine. For this force, what is the potential energy? The potential energy is basically minus gmm over r. That's it. Take derivative. Take the first derivative of this guy. Del u over del r. What you will get? These guys are constant. Minus 1 by r would become 1 by r squared. It becomes gmm by r squared. Isn't it? U is, you may just say, choose it plus. Over here there is minus. And then I have this relation F is equal to minus del u by del r. Because this is force. Force becomes del u by del r. It simply says that if you know the potential energy of any force, I can have the relation between potential energy and the force. In some way, give me the potential energy, I will tell you the force. Isn't it great? Therefore, with this kind of comprehension, using the action principle, what is not requirement? I have bypassed the demand of the force. I don't need to know what is the force of my system. What is required is you simply provide me the potential energy and kinetic energy, and I will tell you what would be the force, because this guy is basically tell you what is the most possible trajectory that a particle can take, right? Without even knowing the force. And this is the most important part. We have derived F is equal to m into a without understanding, without using any kind of law. So what is more fundamental? The action principle now become more fundamental, because now you don't require to know the force. You know, because potential energy is a function of r. It could be function of velocity also, right? You just say that there are two particles, they can have interaction, maybe 1 by r cube, maybe r square, maybe some weird function like 1 by r minus r square. You define any type of your function, and I will tell you what is the equation of motion, because I will going to get some kind of a force. Kinetic energy is not going to change. Maybe in different frame, the kinetic energy would be different thing. I'm going to discuss it in detail. But you see, I have this Lagrangian. With this, I know what's my Euler-Lagrange equation. I don't require what is the force, what's the goddamn force. I spit it out. I easily know what is the force. I exactly know how the particle is going to behave, because I will find out the trajectory, and that is what we require. In order to predict something, you just require the trajectory, and force is equal to m into a was providing you that what would be the best possible trajectory. And now from this formulation I know, therefore I don't need to guess any force. Once I know the Lagrangian, the job of force is over. And this is how the complete particle physics, if you have heard that, okay, we have found some different particle, we have found that there could be some different interaction like weak interaction and so on and so forth. Everything has been constructed by using this Lagrangian. You just define that how your system is going to behave under different circumstances, You can construct Lagrangian for anything from GR to quantum field theory to quantum mechanics and blah blah blah, whatever you may just work with string theory and so on. You can go anywhere, my dear friend, and there is no single problem. So with this tool in our hand, we are going to understand how this powerful thing, how this powerful Lagrangian is going to connect ourselves with the concept that is very important for us in quantum mechanics. So we just leave here with this lecture 1, and in our later video I'm going to discuss with the Hamiltonian approach, and from there I will try to give you notion that okay, if we have these things in our bucket, then we can construct theoretically the so-called Schrödinger equation, so-called quantum mechanics. But it's not a very easy road, and I'm telling you it's not going to be too much difficult. Just stay with me and you are going to learn everything as if it feels naturally, right? This is Saddam Cap signing out, and thank you for watching my video.